Hello. Last time we have introduced the concept of Minkowski spacetime, and we have done a picture of the light cone. It was just like this. Here we have the space, just only one dimension, movement along a straight line in one direction. And here we have the t expressed not in seconds or in year or in something like that, but expressed in space, because the product of the speed of light times the ordinary time is just a space. It corresponds to the space traveled by light in the specified time. Suppose that you have 1 year along this curve. This corresponds to the distance of one light here, because it is just the product of the speed of light times multiplied by the time. Okay, this is the situation, and we said that all this portion of space-time and this one as well are forbidden for the point in the origin of, sorry, let's break it. So this is forbidden. This is forbidden. The meaning of forbidden is relative to the point O, to the origin, to the point that is the event. This is the event. Here now, that is x equals 0, that means here, and t equals 0, that is now. Okay? This region here is the past. That means that is the collection, the set of all those events then that can in some way affect the point O. All these events here are potentially connected with the event in the origin, because as you can see, all these straight line here are all with an inclination that it is less than 45 degrees. This is 45. Okay. For the same reason, we can consider this portion here as the future of the point 0, 0, because all the events belonging to this part of the light cone are potentially connected with the origin, because you can reach them with lines that are less than 45 degrees inclined. The limiting situation is the 45 degrees angle that corresponds to the light. So we can say, for instance, that when we look in a certain direction, and we see the Andromeda galaxy that is 1 million more than 1 million light year distance from us. Okay, in this case here we see something that is here. This is the Andromeda galaxy. Okay, because it is along the light limiting ray in the space-time. It is in the past. Okay, what we see looking at the Andromeda galaxy in the sky right now, it is the image of the Andromeda galaxy coming from a distance of 1 million light years, that is this distance here, but coming from a 1 million light years distance sorry, the distance is here. The distance is 1 million light years, and the distance in time is the same, because when expressed in the product Ct is just 1 million light year, but the corresponding time t is equal to 1 million year. That means that when we look at the Andromeda galaxy, we see an image that is 1 million years old. Okay, this is quite impressive, but it is true. Okay, so in the same way, we can say that if we want to send a message to aliens living 100 or 1000 light years distant from us, we need 1 million year in the future. So we send a radio signal traveling along the 45 degrees straight line, and it will reach this planet distant 1000 light years in a time t equal 1000 years. Okay, it is impossible to do if we don't invent something like teleportation. We cannot send anything faster than light. Forget a spaceship. A spaceship will reach it eventually in a longer time, because it must travel with an inclination that is less than 45 degrees. Remember that in any case, this is the time of the observer at rest in the 0, position. For the spaceship traveling along this line, as we have seen, that the proper time is equal t to the square root, multiply the square root of v square over c square, if you remember. And so the 1000 years, sorry, in this case, suppose it's 2000 years to reach this planet for a spaceship, but this is the time measured on the Earth at rest. For the spaceship traveling, an astronaut will experience a contracted modified time with the Lorentz factor. Okay, but forget it for the moment. So this is the Minkowski space-time representation. Good. Just to go on a little bit, I would like to show you an important important result when we work with this approach. Okay, suppose for a moment, suppose that we are not in the space-time, but in the ordinary two-dimensional space, x and y, okay? The plane, the surface of this blackboard, exactly. Here we are. Okay, and suppose that I've got 2 points, A and B. If I want to express the distance between these 2 points, suppose that this is a rigid rod, okay? And I want to express the length of this rigid rod. What do I do? Okay, I know I take the coordinates xa and xb and ya and yb, okay? These are the coordinates of the points, but I can easily see that this segment here that corresponds to the side, the horizontal side of this right triangle, okay, it is, let's call it delta x. Delta means the variation, the interval of x. This delta x is simply equal to xb. Xb is from here to here, is the coordinate value. Xa is this, so this is xb minus xa. In the same way, delta y, it is yb minus ya, okay? And we know that, let's call delta s the length of the AB rod. We have got, for the Pythagoras theorem, that delta s squared is equal to delta x squared plus delta y squared. Very simple indeed. Okay, let's see what happens if we change our perspective and we look at the Minkowski spacetime. First of all, let's do this important consideration. The length, how do you say length? Length of a rigid rod in the ordinary space is invariant in case of translation and rotations. Okay? What is the meaning of this sentence? Is that if I've got a rigid rod, suppose this little chalk, piece of chalk, okay? If I have this chalk here in the space, if I translate it, its length doesn't vary. If I rotate it, or contemporary, in the same time I rotate it and I translate it, the length, the distance between of the two extreme points of the chalk doesn't change anymore, anyway. So this is exactly the meaning of this sentence. The length of a rigid rod in the ordinary space, two-dimensional like here, or three-dimensional, that doesn't matter, is invariant, doesn't vary in case of translations or rotations. Okay, this is obvious. Rigid means that I cannot deform it, just has to be perfectly rigid. Okay, so what about the distance between, instead of two ordinary points in the space, let's go to see what happens if I consider two events in the space-time. Okay, first of all, we have to say that the length of a rigid rod, it is not an invariant in the space-time, in relativity. Because we know that the length of a rigid body, or the length of a certain distance, as measured by an observer at rest, is different. It's not the same of the distance, of the same distance measured by an observer on board of the moving object. If you remember, we have seen that the length measured by a standing still observer is equal to the proper length, the length measured by the, suppose that this is the rigid rod and we have a person moving, standing on board, okay, and here we have an observer at rest, okay. We know that the L as measured by this man here is equal to the proper length L0 measured by the man on board multiplied by 1 minus v square over c square. Okay, so this is true in relativity, so the length of a rigid rod is not invariant for translations, because you move with a certain speed, and if I measure standing still, the length that I measure is different compared to the distance measured by the moving person. So we cannot use the same kind of invariance. Let's see what can be invariant. Let's take our Minkowski space-time. Okay, and let's work on the let's take two events. Let's call them, just to distinguish between A and B, that were in the pure space plane. Here we have a space-time, and these are the two events, P and Q. P is at a certain position in the straight line at a certain time, and Q the same. In the same way as before, we can build up this rectangle triangle, but the space-time distance between these two events, it is not obtainable by a normal Pythagoras theorem. We know that we cannot have a conservation, an invariance of the length alone, so we must have a sort of invariance of a mixed combination of the two. Let's see what happens if I try. Let's adopt the method of trial and error. Suppose that we imagine that the delta S square, it is a sort of Pythagoras theorem, but instead of using the, let me start, let me write here, okay. Suppose that we write something like this. It is delta ct, it doesn't matter the parentheses, c is constant, so it doesn't vary, and so this is the same like c delta t square, that is this, the square of this side here. The Pythagoras theorem should be plus delta x squared, but let's guess that is minus delta x squared. If we define the space-time interval between the events P and Q in this way, instead of the plus here, we see that something right and very interesting comes out. Let's see. We have to prove this one. Okay, suppose that x and t are the space and time coordinates, so this is the x position of a rocket traveling in a straight line in the x direction with speed v, okay, and the observer on the Earth measures this distance x and the time t. These are the space and time coordinates as measured by the man on the Earth. Okay? Well, we know by definition that the speed v is equal by, as measured by, again, by the person at rest, is the ratio between the variation of position, delta x, divided the interval of time during which the variation happens. So suppose that it moves from x to x plus delta x, this is delta x in the interval as measured by him, delta t, the speed is exactly this, is delta x over delta t. Well, but let's use the formula that we have guessed for the interval, the space-time interval, as measured by the man on the Earth. So we have that delta S A Earth square is equal what? Is equal to C delta t square, that is equal to C square times delta t square, minus delta x square. But I can write from this simple formula, I know that delta x as measured by Earth is equal to v times delta t. So in the place of delta x square, I can write the square of this, that is v square times delta t square. Okay? This is equal, let's factorize, let's collect out the term c squared delta t square. Let's do step by step. I can factorize delta t square times c square minus v square. You can check that if I multiply, I've got delta t squared times c squared, that is this, minus delta t squared times v squared, that is this. Okay? And then I factorize again a c squared from inside, and I've got at the end out, I've got delta c squared delta t squared multiplied by 1 minus v squared over c squared. You see that if I multiply back, I've got c squared delta t squared times 1 is equal exactly c squared delta t squared minus c squared delta t squared times v squared divided by c squared. I simplify the c squared and I have got back this term here. Okay, well, so delta s squared, the square of the space-time interval between P and Q, the two events, that is just the position of the rocket here and the position here, after a displacement delta x, is equal exactly this. So if I extract the square root, I've got this. Square root of delta SE square is delta SE equal of the square root of this, that is C delta T, times the square root of 1 minus V squared over C squared. Okay, this is the interval of this event, between these two events. So the rocket moving from here to here as measured by the Earth observer. What about the rocket observer? This is the rocket area. So delta S R rocket square, it is equal what? It is equal to c square times delta. What is the time of which is the time of the astronaut on board? You remember, is the proper time that we have called tau square, tau. So this is, instead of delta t square, he measures delta t square minus delta x. But what is the displacement of the observer on the rocket? Is 0, because he is on board, so he doesn't measure any movement in his reference frame. So this second term here doesn't exist in this case. So that's all. Well, but now we can see that if we assume that the space-time interval is invariant, this is the same as measured by all the inertial observers, so the man on the Earth and the man on the rocket, we must have that delta S on the Earth must be equal to delta S in the rocket. This is the fundamental assumption, the invariance not of the length of the rigid spaceship, but the invariance of the space-time in distance, the space-time interval between two events. And if it is true, it means that delta S E, that is this one, oh, I cancel this because otherwise it's difficult. So we have got that delta SE, that is this one, C delta T square root of 1 minus V square over C square must be equal to delta SR. But delta SR is simply the square root of this, that is C delta tau. Let me simplify. I can divide by C both, and I've got the important result that delta tau is equal to delta T times the square root of 1 minus V squared. But we know this. Do you remember? This is the time dilation that we have. It has been our first formula in the first lesson, or the second one probably, when using these two light clocks, one still and the other one moving, we calculated the time dilation. So the proper time of the moving observer is equal to the time for the person at rest multiplied by the factor, the Lorentz factor 1 minus v squared over c squared. And this is true. We know that this is true because we have found it in another way, completely different, without assuming any space-time, any Minkowski space-time. But this time, we found it back assuming just this important condition, and together with the definition of space-time interval. Okay? Very, very important. We will use extensively this formula here, and this fundamental result, because in this way we can assuming the invariance of the space-time interval, we can work with different observer in a very, very strict way. As we have seen, most of time we will consider a moving observer, and for the moving observer there is no delta x squared, so this side here is simply c squared times delta tau squared. So we can write this expression here also simply in terms of the proper time. We can divide by c squared as well. And this is another way to write the previous expression. It is a relationship within the proper time and the rest time of the still observer, and the measure of space as made by himself. Okay, I think that is enough for now. It's very important to remember. Just I want to leave you with the last picture. Reassuming everything. This is the Minkowski space-time. Oops, sorry. The light cone, okay, and the space-time interval, okay. Very important to notice that the space-time interval between two events along the 45 degrees line, this is the forbidden area. So this is the light travel, the light beam, okay, 2 points standing on this line. Suppose the origin E is a certain point P, okay. Which kind of space-time distance do they have? It is 0. You can see, because the distance delta s squared is equal to c squared delta t squared minus delta x squared. But delta x squared, let's do like that. This is equal to let's factorize delta t squared. So it is c squared, okay, minus delta x squared divided by delta t squared. You see, if I remultiply, I get c squared delta t squared minus delta x squared. But this one, this guy here, is just delta x over delta t squared, but delta x over delta t is the speed of the moving object. But in this case, we are considering the light, a photon. And for a photon, this is exactly c squared. And so when you substitute, you see that it's c squared minus c squared, that is 0. Okay? And so the interval in space-time between O and P, it is 0. Okay? In this sense, we can say that for a photon, there is no time passing traveling in the universe. So he lives and arrives at a certain distance galaxy in the same time. Okay, thank you. I don't want to add anything more, and see you next time. Bye.